will also then talk about this program that I talked about, RSET, and then we'll summarize today's talk. I just am curious, you can unmute yourself and tell me if you have been using any remote sensing data for your research or applications.
Yes, ma'am, we are using remote sensing data.
Okay, and so some of this might be familiar to you. This is NASA Earth Science website. As you can see, the mission is to help understand our planet's interconnected systems. And for that, the goals are to design science and technology for building aircraft-based and satellite-based instruments, launch airborne and space missions for Earth systems observations, then collect and analyze these observations, and then develop ways to put this information to use for societal benefit. So these are the major goals of NASA Earth Science. And for that, everything that is developed, it goes from technology to research to application. Yeah. So these are the focus areas, as you can see. Atmospheric composition, so air quality is a major part of that. Weather and atmospheric dynamics, climate variability and change, water and energy cycle, carbon cycle and ecosystems, and Earth surface and interior. So for all these focus areas, missions are planned so that proper observations or appropriate parameters can be observed from space, and then they are used for understanding the climate system. Recently now, the focus again is on freshwater availability, on food security, and also on natural disasters. These are some of the theme areas that NASA is focusing on currently for applications.
Ma'am, sorry to interrupt you. What do you mean by food security, ma'am? Sorry to interrupt you,
So food security, okay. So basically, when it says food security, it's basically using remote sensing and model data to understand and predict crop yields, also droughts, or any extreme weather and climate situations that you can monitor, that will help in making decisions or managing food security for coming years. So that's what it is. Basically, just observe crops. There is a program that now is using remote sensing data for crop identification from space, so to look at yield based on remote sensing data. So if there are no in situ data available over large scale, you can monitor crops. So that's what it is. Overall mission of climate variability and change area is to measure and model Earth's dynamical systems and how they change over time, and for also support interdisciplinary research to better describe, understand, and predict interactions among Earth's ocean, atmosphere, land, and ice, and how they all influence Earth's climate over a wide range of timescales. So this is the overall goal of climate variability and change focus area. And for that, so what we are going to do today is just talk about of all these focus areas. And if you go to this website, you will have a lot of information. You can click on each of these focus areas to understand more. We will focus on satellite data and models which are useful for climate variability and change, and water resources. These two I'm going to focus on. So talk about satellite data and models which can be used for studying these topics. So climate variability and change, or CVC as it's known here, it's basically these are major thematic areas, as you can see. So the questions are, how can predictions of climate variability and change be improved? What is the role of atmospheric composition and clouds in the climate system? What changes are occurring in the mass and extent of Earth's ice cover? How does global ocean circulation vary on a variety of temporal and spatial scales in response to climate variations? And how is global sea level impacted by natural variability and human-induced changes in the Earth system, and how we can predict these changes. And so these are the overarching questions. And so for that, whatever measurements are needed in ocean, land, and in cryosphere relating to ice, for that, missions are planned as well as models are developed also. And so the overall goal is to produce climate data sets from satellite observations to understand and address these questions, develop Earth system models with satellite data assimilation, and make the observational and model data open source and publicly available so they can be used for research as well as applications all over the world. That's the goal. So with that, we'll start with overview of NASA Earth system models and remote sensing data for understanding climate variability and change. And we'll focus again on water component in that. Okay, so this is a fleet of NASA Earth system, but all the satellites are shown here. As you can see, these are all the current satellites shown here. These are over here, as you can see, there's a legend given. So these are in implementation. Then there are primary operations and extended operations. So these are all extended operational satellites, which are very useful for monitoring long-term climate variability, excuse me, and change. So we will talk about some of these satellites, especially related to water resources. But then you can also see that there are satellites which are focused on water quality, on surface water, ocean topography. There is also the ocean observing satellite planned. There is water quality hyperspectral instrument planned. There is air quality monitoring, also solar irradiance monitoring, and this is NISAR, which is upcoming in 2023, I believe. That's a NASA-ISRO joint synthetic aperture radar satellite that will be launched in a couple of years, and a lot of research is already going on in that area. There are other joint satellites with NASA and NOAA. They're joint polar orbiting satellite systems, so JPSS. These are also currently flying, and there are future missions planned. If you see, we'll talk about this current satellite data, but the one that you may find useful and maybe using already is Landsat. So it continuing mission, Landsat 9, is also planned. And so let's go look at some of these satellites, how they can be used for monitoring water components. Okay, so we'll talk about specific freshwater components here as listed. How can we monitor this from satellites? So start with rain. So the two satellites, and I'm sure most people in India, they know about these satellites because precipitation and monsoon, they're so important. So TRIM, which is Tropical Rainfall Measuring Mission, and Global Precipitation Measuring Mission. These two satellites, which are joint missions between NASA and JAXA, which is Japanese Space Agency, so TRIM was the first satellite that carried a microwave radar in space. And GPM then improved and has a dual frequency radar also. So these satellites now provide precipitation records based on microwave radiometer as well as radar. Second freshwater component, if you want to talk about, is evapotranspiration, just as important. And that can be derived from these three satellites. We'll talk about that: Landsat, Terra, and Aqua. Soil moisture, there's a not so old SMAP, a soil moisture active passive, that was launched in 2015. Then there is groundwater data available from GRACE and GRACE follow-on satellites, and also reservoir height data. They are available from JSON altimeter data. There are actually goes back from Topex Poseidon, but Jason 2 and 3 are currently flying missions. They provide reservoir heights in many reservoirs, at least bigger than 50 kilometers square, that they can provide a height of reservoir water level. So again, this is just talking about what temporal coverage of all these missions. So TRIM and GPM combined, they cover data starting from, say, 1998 to present. So precipitation data are available for more than 20 years now. Landsat mission is the longest flying mission, started in 1972, and it's continuing. It's high resolution data for land observations. And also it is now used for water quality monitoring as well. The current satellites which are flying are Landsat 7 and Landsat 8, and they provide information from 1999 to present. And as I mentioned, Landsat 9 will be launched pretty soon as well. These two satellites, Terra and Aqua, these two missions also are long-term missions from 1999 and 2002 respectively. So they also provide close to 20-year observations now. SMAP, 2015 to present, and GRACE and GRACE follow-on, they provide data from 2002 all the way to present. There is a little gap in between, but more or less continuous data, ground water or terrestrial water can be obtained from these two satellites. And then Jason 2 and Jason 3. But this record, also altimeter data, go back to 1992. So these satellites provide almost all freshwater components that you want to observe. Most of them all of them are global data, except for TRIM. And of course, runoff, which is also a very important component that cannot be observed directly, but it is derived from hydrology and land models. So in which some of these data are assimilated. So coming to Earth system models. So here is just a schematic of how these numerical models are used, in which surface measurements and in situ measurements all are used, assimilated. Also, satellite data are assimilated. So it's a value-added system for climate and water data. And what we want to talk about is a number of models which are available for looking at various timescales, looking at climate variability and also long-term climate variability and change. Okay, so here is again a table. So you can use this as your reference in future if you're looking for any of these data sets. So in addition to what we talked about, this lists all the sensors which we don't have a lot of time to go in, but at the end I will provide you a link where you can go and know more about all these sensors. So again, for precipitation, it's basically microwave radiometer and radar. Terra and Aqua MODIS, which is a lot of people in India use that, moderate resolution imaging spectroradiometer. It's a versatile instrument with visible near infrared and middle infrared measurement. So it's used for land, atmosphere, ocean, all the different bands can be used for that. So in this case, for evapotranspiration for snow cover, especially if we're talking about water budget components, these measurements are very useful. Landsat has thematic mapper or enhanced thematic mapper and operational land imager, also with visible near infrared and middle infrared, thermal infrared spectral radiances that you receive. Can be used for evapotranspiration primarily when you talk about water, but it's also used heavily for land management and observing vegetation and land cover, etc. SMAP is a microwave radiometer, and it's L-band radiometer and measures soil moisture. GRACE has a microwave radar, K-band radar. There are two tandem satellites. They fly around the Earth and measure gravitational change. And based on that, terrestrial water is derived. And from that, then groundwater is derived. JSON series of satellites, they are C-band and Ku-band altimeters. They are used to get lake reservoir level heights. So we'll focus a little more on precipitation because it is so important. And then, so what I'm going to do now is talk about specific data sets that can be used. Have you used TRIM or GPM precipitation data? Anyone? You can unmute yourself.
We have used a TRIM data model for one of our work.
Okay. So we'll talk about precipitation data, evapotranspiration data, soil moisture, and groundwater data, and then a few models where you can also get runoff so that all the water components can be obtained. Okay. So here, let's see, TRIM and GPM. As I mentioned, they're satellites, mostly with they're microwave radiometer and radar, but they are used in conjunction with a constellation of national and international satellites. And so TRIM and GPM measurements, microwave observations, they're used for calibrating microwave radiometers or imagers on other satellites which are available around from different agencies like NOAA or other, like Megatropic was part of a constellation also when there was a radiometer that it didn't work, but then there was an imager that is still working. And so based on these multiple satellites, there is intercalibrated multi-satellite product that is produced, and that's called TRIM Multi-Satellite Precipitation Analysis, or TMPA. TMPA now, it's extended the similar concept about iMerge. It is integrated multi-satellite retrievals for GPM. So very similar concept. The multiple satellites are used, and as much possible microwave observations are used. If there are data gaps at higher latitudes, then infrared observations are used to fill that up. But so this is a very important data set if you are we want to work with long-term precipitation record. It is already used for many applications, especially for hydrologic model forcing, flood model forcing also. Okay, and so iMerge, because this might become very useful in monitoring rainfall in different time scale. So there are multiple products. There is early product, which about 5-hour latency, which can be used for monitoring flash flooding. There is also a late product that's about 12 hours latency, and that's used mostly for crop irrigation or monitoring whether there's going to be any rainfall in next 12 to 24 hours or so. And then finally, there is a research quality product that is put out after 3 months. So there's a 3-month latency, but this data, in addition to satellite-based precipitation, land-based rain gauge data are also used and merged with them. And so these are more or less research quality product. And let's see, the summary is given here. TMPA, which was available at 1/4 degree resolution in 50 south to 50 north latitudes at 3-hour interval. iMerge has improved that with 1/10 of a degree resolution Currently, it is covering 60 south to 60 north, but it will be available pole to pole very soon. And the temporal resolution is every half hour. Every half hour, you get an image. Now, there is a new product that came out last year. Okay, this is the first long-term precipitation data based on microwave radar and radiometers. So combining TRIM and GPM observations, so TMPA and iMerge, they have been extended back to June 2000. So this is really a about 20-year data set that can be used for understanding climate variability during this period. Okay. Then moving on to evapotranspiration. So there are 3 different products that can be used at different resolutions. So one is from MODIS. MODIS-based data, these are standard products available at 500 meters every 8 days. And they started so production started in 2010. So about 10 years of data are there based on MODIS. Landsat-based data, they are also available at 30-meter resolution. As you can see, individual field farms or fields can be seen from Landsat. Just an example is shown here. And there is a website that you can use to get this data. So each product, it also gives you a website where you can get this data. And so here's just an example I was looking at yesterday over India, that you can pick a Landsat tile and calculate evapotranspiration in millimeters per day from this metric evapotranspiration data, which is available on Google Earth Engine. So this is a quick look, and you can also download this data in your own region if you're interested. Yet another evapotranspiration data that has come out now is a combination of MODIS and Landsat, and also some geostationary satellites are used. So right now, it's available only over the US, but it will be available globally soon when all the geostationary satellite data are calibrated with MODIS and Landsat sensors. It's called LXC. It's Atmosphere Land Exchange Inverse LXC. And you can read more about this data set in this document. This has, what happens is both MODIS and Landsat, being optical sensors, are used here. When it is cloudy, it is very difficult. You don't see the land. And because of that, when multiple sensors are used together, there is more likelihood that you can catch clear sky conditions and then look at the land. So this is an improved product compared to the previous 2 that we just talked about. And the next one is soil moisture from SMAP. This is available at 36 kilometer and 9 kilometer resolution. And it takes 3 days to get global coverage. It's available for last 5 years now. Now there's also a combined product which uses synthetic aperture radar from Sentinel-1, which is a European Space Agency satellite. And so combined data are high resolution. Just radiometer provides data at 36 kilometer. Okay. Finally, GRACE terrestrial water storage data. So this is relatively a lower resolution sensor. So grid size is about 300 to 400 kilometer, depending on which methodology you use to desegregate data from satellite. So about 150,000 kilometers square. So relatively coarse resolution, but it provides a large scale variation in terrestrial water storage. So the data are gridded at quarter degree or half a degree resolution for convenience, but this is the original resolution. And there are also tools and portals where these data can be obtained. So I'm giving all this information so later on I can share these slides with you, and you can use them as a reference presentation. Go to these sites and get more information, and also download data for your own region if you wish to. This is an interactive tool that shows anomalies in terrestrial water or groundwater in this case. So this is over India in May 2020. As you can see, these are anomalies going from minus 30 centimeter to 30 centimeter. And as you can see in northwestern India, southern India, also in eastern India, except for in central India, more or less you see deficit in groundwater in this month. As you go forward, you would see, if you go through this tool and look at the time series, you will see it does vary. After monsoon, you will see some of these anomalies decreasing, but every year in spring, summer, you do see this depletion of groundwater over majority of India. Okay. Now, again, these are some of the, so we talked about satellite data, precipitation, evapotranspiration, soil moisture, and groundwater. We're moving on to Earth system models, which are available. So GEOS 5, which is the Goddard Earth Observing System version 5, this is used in a MERA, it's called Modern Era Retrospective Analysis for Research and Applications. So this model, GEOS 5, is part of MERA, atmospheric model. So they provide atmospheric model current as well as 10-day forecast. And GEOS 5 is also used for, now they're setting up for decadal prediction also. So these two models are there. Then these are land surface hydrology model based on water and energy balance. These are GLDAS, so Global Land Data Assimilation System. And this is North American Land Data Assimilation System. We'll talk more about GLDAS. And finally, there is a Goddard Institute of Space Studies, GISS Model E, which is a coupled climate model. Okay. So brief information about MERA. What it does is it blends vast quantities of observations from satellites available all the way back from 1979 to present. So over the years, observing system has changed, as you can see. Before, this is 1973 to 77, no satellite data were there, just in situ observations, surface-based data were used for assimilation. As you move to 79, then polar orbiting satellites started coming up. There was also geostationary satellites over the US. And so they started assimilating those data. Then 87, you come here, there are more observations. And now 2006 to present, almost entire Earth is covered with a lot of satellite data. So these data are assimilated. And so MERA, current MERA system, MERA 2, data are available from 1980 to present, and it's going to go forward. So it's a almost 40-year long data set that can be used to understand climate variability. And so it provides state-of-the-art analysis, and also it focuses on improvement of hydrologic cycle particularly. Then GLDAS, which is a water and energy balance model, as I mentioned, it assimilates remote sensing data, and they're forced with TRIM data and now GPM also currently. Weather data are used from a variety of models. Vegetation information for surface, it's used from MODIS, and cloud and snow information also from NOAA, and this is SSMI, if you know, the instrument is used for that. And there is integrated output that you can get is soil moisture, evapotranspiration, surface and subsurface runoff, and also snow water equivalent. Last two, which you really cannot observe directly. So this is the only way to get these two components if you want to look at overall water budget in any area, then GLDAS is a good model, and now it's available at quarter-degree resolution. Okay, so this is NASA Earth Science Data Access. There are a number of web portals and tools that you can use to search and download some of these data sets. And so here is a summary of that. This is the website, and you can search, find data. There are a number of other data repository sites that are shown here. Once you go to NASA Earth Data, you can explore each of them. So some of them, they provide just land data, some provide atmospheric data, some ocean data, and there is also socioeconomic data center called CDAC. So you can explore these centers to get different data sets. Okay. And so again, focusing on water part, specifically rain data can be obtained from these sites. They're just, you can click on them, and they're self-explanatory. There's a lot of information. So there is precipitation measurement mission site. Also, there is a site, some of you may be familiar, it's called Giovanni. Has anyone used Giovanni in your group?
Yes, ma'am. We have used Giovanni to access the precipitation data for local regions.
Okay, that's great, because even this is a great educational tool also. Students can explore various data sets. Without downloading, you can do an online analysis. So I would strongly recommend getting more familiarity with this particular tool, and I'll be happy to show a snapshot of it later on. Okay, so for snow cover, again, there is a National Snow and Ice Data Center. They provide MODIS-based data. Then soil moisture, also from NSITC and from Giovanni, you can obtain this data. Land cover and normalized difference vegetation indices from Landsat and MODIS. These can be available from Earth Explorer site. Also, there is a Appears tool that allows you to easily explore and download this data. You can upload your own shapefile or polygons or in these sites and download data. So you don't have to download global data. You can also convert these data. So original data are in HDF or NetCDF format, but through some of these tools, you can convert them to GeoTIFF if you want to use them in GIS. Again, Giovanni, almost all GLDAS is available there. GRACE data are available from JPL sites. These you can go and just download data. And altimeter data are available from Foreign Agriculture Service site. It's shown here. So all these data are very easily available. You can subset them spatially and temporally as well. Finally, GIS Model E climate model. This is it's a series of coupled atmosphere ocean models. So they include all components: atmosphere, ocean, sea ice, and land surface components. They have interactive atmospheric chemistry and aerosols, carbon cycle, and other tracers. And this is a part of this climate model intercomparison project. So they're included in CMIP 5 and CMIP 6 now as well. Also important to note here is that data from GIS Model E, they're available. Also, model code is available. It's free. There is a little bit of learning curve, but you can download the code if you are interested in running this model or implementing in some way. Okay. And so if I have time, I will share this site with you, but this allows you to monitor surface air temperature over several years. So otherwise, just if you go to this site, you will be able to see how surface temperatures have changed over years, starting from, so this is the last period, 2017 to 21, but we'll look at this. Okay, this is the site where you can download Model E data. As you can see, there's a temperature, aerosols, clouds, precipitation, radiative fluxes, and there are some impacts data, such as there is agricultural intercomparison project data are available here as well. There is one more resource. This is NASA Climate Change Portal, focuses specifically on climate change. And so that also, if we have time, I will just demonstrate this also, just to show you what information is available. You can look at temperature data, sea level rise data, also snow cover data in polar latitudes you can monitor using satellite data. So what are some of the advantages of using these data? So first of all, remote sensing and modeling data that we just talked about, they are near global in coverage compared to surface-based data, which are non-uniform. There are areas, vast areas, which are data void. You don't have all these measurements. So there, remote sensing and these modeling data can be used. Wherever there are surface-based measurements, they augment these data, and then you can validate nicely how satellite and model behave in your area. If you have surface-based measurements, it's easy to validate, or at least understand if there are any biases or errors in these data. Also, when you assimilate satellite data into models, you can then have uniformly graded, more frequent in time data sets that's easier to work with, especially if you want frequent information about, say, water budget components, then that's useful. Also, evapotranspiration and runoff, something that is not very easily observable, can be obtained from these modeling systems. Okay, all these data are free and open source, and here actually it is more than 20 plus years of data are now available. Some of the challenges to use this data are, and again, this is focusing on water, but that's any climate data that we talked about. They're from different satellites and sensors, which have varying spatial and temporal resolutions and coverage, and quality also differs. So it's not easy there is a little bit of learning in using each and every data set and understanding what the quality and accuracy of these data is. It's very difficult to get high quality in spectral resolution, temporal resolution, spatial resolution, all three high quality, it's difficult. So there is some trade-off depending on why you want to use this data. And then satellite and model data, these data, they're large files, different formats. You have to get them from different portals. So for that, a little bit of training is required. But once you get used to it, it's pretty easy to access them. So generally, they are validated. There are NASA and other space agencies also have ground validation programs. And so all the satellite missions, they have their validation programs, but they're not global. They're in selected regions. So for your own region, it's a good idea to have assessment of these data sets before you, to assess accuracy in your own region, because they're not validated everywhere. So you don't know how accurate they are everywhere. Oftentimes additional processing may be needed to use any of these data sets we talked about. So there are some challenges, but there are really advantages which are, so these challenges can be overcome. So next two sections, what I want to do is just show one example. We did an in-person training in India, in Dehradun, in one of the ISRO centers. This was in 2018, and that was focused on flood monitoring using optical, microwave, passive and active data, and also including SAR. So at that time, there was this flooding in Kerala, and that is what we did a case study on. So this is in August 2018. As you can see, this is from GPM. You can see how precipitation peaked in this area. Almost daily precipitation was about 40 to 45 millimeters in these 2 days. This is again integrated over entire state, and then this is accumulated rain between 14th and 15th of August on 2018, again from GPM. And as you can see, these data are in millimeters as well, almost more than 330 millimeters in many areas. Everywhere it was about 150 millimeters in this period. So this heavy rain caused flooding. There are also flood monitoring tools. There is a global flood monitoring system that uses TRIM and GPM data in a hydrologic model and a river routing model to come up with flood detection intensity and flood intensity detection, and also looking at stream flow in various rivers. So as you can see, this is above threshold flood depth in millimeters, and it shows where flooding occurred in Kerala in that period. So this is 15th of August. This is every 3-hour data are available here. And MODIS-based surface inundation was noted also. This is also a tool that can tell you where inundation occurred. So when actually there's a lot of rain, you probably cannot see the surface, but what happens is as soon as this rain clears, or then you can see the surface and look at inundation surfaces, so you can plan if there is any relief or rescue operations needed post-flooding. So that this shows the same in this region where there was major flooding outside these river channels. Excuse me. And then I want to share, let's see if I can show you an animation of I want to show this GPM iMerge. Using this Giovanni tool, you can do animation, and that is what excuse me. Excuse me. So this shows half-hourly iMerge precipitation in millimeter per hour, and it shows tropical cyclone Amphan moving towards India. So you can monitor a system that any storm that is arriving, using iMerge every half hour, also using this Giovanni tool that I just mentioned. So finally, I want to talk about NASA, that remote sensing training program. So far, we started with NASA's focus areas on Earth system science. Climate variability and change is one of them. Also, water resources is one of them. And we talked about a number of satellites, what kind of data sets are available and where to get them. We also talked about models. And to get training in how to use this data, NASA Applied Sciences set up this program, Applied Remote Sensing Training Program, that I am a part of for more than 10 years now. And I conduct trainings mostly on water resources and disasters, hydrometeorological disasters. And these, so the website shown here is the RSET website. So the goal here is to empower just global community in using this open source data. So far, RSET provides training in these 4 areas, so water resources, air quality, disasters, and land management. And the goal is that can we use this data for environmental management or decision making? And so RSET started in 2009 with air quality trainings. But as you can see, by now, all the themes, air quality, water resources, disasters, and land management, all the circles shown here show how many people were trained in each year. So overall, since 2019, combining all the themes, about 40,000 participants have taken RSET trainings from about 170 countries. And close to 150 trainings are now conducted. About 9,000 plus organizations have participated. And as you can see, disasters and land management, they have become more popular in last 2 to 3 years. Also has water resources. So RSET can conduct in-person and online trainings in one of these areas, so they could be very introductory and general. You don't have to have any remote sensing knowledge. So we start with very basics, or it could be very advanced, very specific, something like we did this in Dehradun a couple of years ago, where most participants, they know about data sets, but we then will work with applications of the data sets. So you can go to this website. Currently, there is a webinar going on monitoring urban heat island. There will be one upcoming in January that will be focused on reservoir height monitoring. Sorry. So to summarize, we talked about NASA remote sensing and modeling data, which are available for 20 plus years, some for 40 years, which can be used for all the way from near real-time weather applications all the way to interannual and longer climate variability. So this should be GEOS 5. GEOS 5 model provides decadal timescale predictions as well. And Model E provides climate projections if you are interested. All these data and web tools, they are open source, and RSET can provide online and in-person training if you are interested. So with that, I will end this presentation. I thank you for this opportunity, and if there are any questions, I'd be happy to answer them.
Thank you, ma'am. Thank you very much for your wonderful presentations about NASA activities on climate change. Thank you, ma'am. Participants, please interact with the ma'am.
Yes.
Thank you for the presentation. I have a question. Is RSET open?
Yes.
Is RSET open for everyone, or is there
it's open for everyone.
Oh.
It's open for everyone.
So
and
it's
like
free
a series
too. Series of presentations going on all over the year.
Yes. So if it is introductory webinar, it's mostly presentation and demonstration. So like we would walk you through any of these tools, how to download data. There are advanced trainings where there is hands-on computer-based exercises are provided. And if you go to RSET website, and I can perhaps share that with you so that I can walk you through. Okay, so this is the website, and you can go through all these themes. Right now, there is upcoming webinar also in this black marble nightlight imagery from Nova Weir's satellite. So this is useful for if there's power outages. You can. Some of them are also given in Spanish. If you specifically look at, say, disasters, urban heat. So all these presentations are available online. You can, and I wanted to show you the one that I recommend if you're interested in. So advanced webinar we did in July, August, was monitoring water budgets in river basins. If you go to this webinar, not only you will see slides, but you will have exercises which were given, which guides you step by step to download data and do analysis using GIS. So now in some advanced training, some Python codes are provided, or Jupyter Notebook sometimes is used also. And more Google Earth Engine based trainings are planned so that people don't have to download data, they can do online analysis.
Thank you.
If you have any other questions. So really the idea for this presentation was to provide information about all these open source data sets that can be used for research and not show so much research results at this point. So if you have any questions about data, I can answer those, or you can look at the references and sites given in here.
And I have a question. You mentioned gravitational data to measure the water level in reservoirs.
Mm-hmm.
So how is it actually measured? How is gravitational data actually related to the measuring water level in reservoirs? How does it work?
So you mean the GRACE data you're talking about, right? Terrestrial. So again, I would say go back to, we did a GRACE based webinar last year, earlier this year. You can go to RSET website and you will see that. But basically there are two satellites which go over the same location. And they are also tracking each other. So because of gravity, when it goes over, say, if there's a um, depth of water that is more, or if there is topography and more gravitational pull because of Earth's mass, satellites get affected by, they get pulled. So when both the satellites pass over the same location, and the distance between them, based on that, they derive how much gravitational change there is, so mass change. And that is, most of the mass change on this time scale is because of water change in terrestrial water storage change. So that it is translated to that. It's not a trivial procedure, and you can go through that in that webinar, or if you go to the website that I provided, there's a lot of information about how they derive actually and what the accuracies are. So all of them, they do have pretty sophisticated algorithm to derive geophysical parameters. And so that is not something that is very trivial, that's for sure. One has to, then you really have to know the background of radiative transfer, or using these data. So is your center or university working with any of these data sets?
Yes, ma'am, we are working.
We have been using Giovanni for trend data analysis. Sir has been working with autoclave matter and quality analysis.
Yes. Okay.
Calypso data, using
Calypso, right. Yeah. So a lot, we did not talk about air quality or land or ocean data. We just focused on just water part of it. But yeah, all these data sets are available.
Participants, any questions? Any interaction?
Yeah, so if you don't have any questions, okay.
That's a question for you from Ramini. I'll paraphrase it for you. During rocket launching missions, due to extreme weather, the launching is delayed. Is there a tool or machine developed that can help in system without help in launch without delay?
Okay, so if the weather is bad, there is no other. What was the question?
The question, ma'am. During rocket launch missions, due to extreme weather, the launch may get delayed. Is there any tool or machine developed that can help in system launch without delay?
No, I mean, if the weather is bad, then of course the launch has to be delayed. That there is no tool to change the weather, of course, but you can have prediction, advanced prediction, so that you can plan. That then you can avoid delay that way. That if you know that weather is going to be bad, you're not going to plan that.
I have a question. Is there any model like WRF model or XM model will help us? Is there any model that is available online to predict a simulation as well as forecasting, like WRF model?
So there is a mesoscale model like WRF, but now new WRF, it's called NASA WRF, it's developed too, that you can use. So the way it is used is that Mehta or GEOS 5 data are used for forcing WRF model. So GEOS 5 and Mehta, they already do assimilation of a lot of satellite data and in situ data, and they are used as forcing for WRF. So that version is available, not online. That's still being developed, but it's there.
Satellite data with in situ data, madam?
Both.
But the satellite data are column data, but in situ data are some different format data. Will it give correct data?
I don't think I think your voice is breaking. I didn't hear the question.
Satellite data are mostly column data, but real time data are that what we are measuring in the real time. How we can match these two data? Will it be a true? We will get a good results.
So no. So you don't always assimilate column data. Only some models, they sometimes assimilate vertical radiances, but most of the time it is still at particular level that you assimilate data. And especially for Mehta type system, at surface, they use this 4D analysis to merge in situ and satellite data and come up with assimilation or analysis for that. So, I mean, it's all being done. It's not something that is available to use without any understanding of that. Also, it requires a lot of computational power just to assimilate everything. If you're doing global, of course.
We have 2 questions for you from participants. I'll paraphrase it for you. If more than one satellites are being used for studying the same parameters, say for example surface temperature, then it must be that it must incorporate data from each and every satellite which collects those data, or it is select specific satellite when selecting the data.
So, I mean, this question always comes up. So, the 2 things to keep in mind. What is the overpass time of the satellite? So, are you interested in daytime temperature, nighttime temperature, daily average temperature? And if you have multiple satellites taking the same measurement, you can actually composite them, use as an average, and also be aware of what the differences are. That would be your uncertainty, that you get. But because unless you have a geostationary satellites, most of these satellites are polar orbiting and they have local time of observation. So there is always some bias when you look at different satellites, or actual signal is there too, because you're looking at temperature at different time of the day. So best thing is to sort of average them, and then also be aware of what range of variations there is. So that tells you how to interpret that data.
Ma'am, we have one more question from Rohini. What is a weather balloon, ma'am? That's okay.
So weather balloon, I'm sure India has a weather balloon launch radios on. So these are basically balloons which fly and then they carry instruments with them, and the sensors they have radiosondes have temperature, humidity measurements, and that, so wind speed and direction. Also they have wind sonde, which has wind sensors also. So temperature, humidity, winds, they're all, and then they're transmitted. So they're collected back. I'm sure there are balloon launch sites, weather balloon launch sites. IMD has several stations where weather balloons are launched with these instruments and the data received. Oh, okay. So Vikram is here and he says that Chennai airport should have one balloon launching facility.
I have a question, ma'am. Actually, very soon we are going to launch that tethered balloon to measure black carbon PM 2.5 some particles.
Right, right.
So I want to measure the meteorological parameters along with the particles. So
Okay.
what type of meteorological parameters I want to measure along with the particles? So what type of instrument that can be used to measure along with the particles in the tethered balloon?
So along with the particles, I think you want to know wind and humidity both, right? Temperature, winds, and humidity, all three you want to know.
So can you suggest some instruments?
Okay, that I on top of my head, I don't know specific instrument, but I can definitely find that information and send you.
Ma'am, we have one more question for you from Karthik.
Mm-hmm.
I'll read the question for you. What if satellites stop working and end up as space debris and continue to orbit and affect all other satellite parts?
So, sometimes, like I know about NASA satellites, that many of them, they have, once they die or they stop functioning, they are guided back. There is a control, they just come back and they burn or they drop in the ocean. So yes, there are so many satellites, they may not be functioning and it's just adding to space debris. But some of the satellites that we talked about, like TRIM, there is always a control, there's a plan that how it's going to end and where it's going to end. So there is also that component. So it's planned that way, that a satellite dies, it's either destroyed or it's burned when it comes back to Earth. So if there are more questions, you can email me as well. I'd be happy to share my presentation slides with you, because it's more or less, it was more information about data and tools or websites, so that if you want to go back and refer to that, so I'll send it to Dr. Vijay Bhaskar, my presentation, and then you can share. So you have all that information. If you have any questions, you can email me as well.
Sure, ma'am. I will be in touch with you. So I think there is no more questions from the participants. So on behalf of the UGC Stride Committee, we thank our speaker, Dr. Amita Mehta, for an excellent presentation on NASA and its role on climate change, especially on evapotranspiration and the hydrology-related studies. Thank you, ma'am. It is an eye-opening session for us. We have already studied a little bit about geo-wind analysis, but this presentation helped us to move further towards the remote sensing data. Thank you, ma'am. Thank you very much for your enlightening address. Thank you, ma'am.
Okay, thank you so very much for this opportunity to talk to you all. And just please let me know if you have any questions or if we can help in any way. So thank you.
Thank you. Participants, thank you for joining us today. The session ends for today. Tomorrow, the session begins at 10 a.m. sharp. Please be available at least 10 minutes before the start of the session. And have a good night. Thank you.